So we have seen how to design an oscillator. Now we will try to understand what is phase noise in the context of an oscillator. So if we talk about an ideal oscillator, let's say this ideal oscillator is generating a perfect sine wave with amplitude A and angular frequency omega naught. This is an ideal oscillator. In reality, this oscillator will be composed of various electrical components, which we have already seen, and those electrical components will also be adding its own electrical noise. This is a real, she also noisy oscillator. This VO dash, if we try to observe the output voltage waveform with time, so because of this noise, the output waveform will not exactly look like that of an ideal oscillator, but it will have some noise riding on top of the expected output. And we can write this output waveform, which is supposed to be periodic, but it has been corrupted because of the noise in a real oscillator. Then one way to capture this effect is by saying that the amplitude of this sine wave is getting perturbed because of this noise. In addition to that, we can also see that the period of this oscillator is also looks like not same as what we had got in the case of an ideal oscillator. So change in this periodicity can be captured by adding some noise in the phase term. So we can write this noisy output as some A plus some noisy component and this phase which was completely linear with respect to time now has got some noise as well. If we observe the zero crossing instance for this noisy oscillator, then we will see that the effective period is no longer same as what we had got for the case of ideal oscillator, but it is sometimes more or sometimes less than capital T. So in general, the output of a noisy oscillator can be written in this form, where this small an captures the perturbation in the amplitude, and this phi n captures the noise in the phase. So this term phi n of t is called as phase noise, and effectively it captures the deviation from the expected linear phase from an oscillator. A few points to note here is, so we will find that this amplitude noise many times is already suppressed by the inherent amplitude limiting phenomena which is present in the oscillator, which we have already seen in the case of the LC oscillator, where the amplitude is maintained to a specific value which is required to sustain the oscillation. In addition to that, this oscillator will be driving the LO switches in the mixer stages. So when we are driving those switches, so again the amplitude noise is not going to result in any effect at the output of those mixers. For this reason, many times the amplitude noise of an oscillator is ignored. The amplitude noise is reduced by the amplitude limiting circuits in the oscillator itself. Also, this oscillator drives circuit blocks which are using oscillator output to result in periodic switching. Rise amplitude noise doesn't affect output. So here when the oscillator is used to result in this hard switching of the MOSFETs, then this amplitude noise is not going to result in any change in the output. Whereas this phase noise, as we can see here, it decides the periodicity of this output signal. So this is really important component in an oscillator output. Phase noise perturbs periodicity of oscillator output. This directly decides the spectral purity of an oscillator. Okay. So assuming that this amplitude noise will be somehow removed either in the oscillator or in the mixer stages, we'll try to understand how this output of a real oscillator will look like in the presence of phase noise. VO dash we can write only in the presence of phase noise as A sine omega naught t plus phi n of t can be written as A sine omega naught t cos phi n of t plus A cos omega naught t sine phi n of t. So this phi n this phi n is the noise in the oscillator output due to the electrical circuits. So we can consider this phi n to be very small quantity. We can approximate this as A sine omega naught t plus A phi n. Here we have assumed this cos phi n of t is approximately 1 and sin phi n of t is approximately equal to phi n of t, assuming phi n of t to be very small. So we can approximately write the output of a noisy oscillator as the sum of the output of an ideal oscillator plus another term which is an amplitude modulated carrier signal, and this amplitude is modulated by the phi n or the phase noise. This is output of an ideal oscillator, whereas this second term is amplitude modulated signal. So now let us take a look at the frequency spectrum of the output. So to find the spectrum, we can look at the spectrum of these two terms. A sin omega naught t. So this is going to have just an impulse in the frequency domain. So to understand the spectrum of the second term, we need to know the spectrum of phi n of t. And since this phi n is a noise, so we will talk about the power spectral density of phi n of t. So let's say the PSD of phi n of t has a low pass behavior, and its double-sided spectrum looks like this. Then we can find the PSD of entire second term. We want to find the PSD of A phi n of t cos omega naught t. So here we can see that this is like an amplitude modulation of this carrier. So this PSD, which is centered around DC, will get up converted to omega naught. So now it is going to look like this. And you can see that its strength is going to be that of S phi n, which is scaled by a square by 2. So it is going to be a square by 2 multiplied by S phi n. Now we have got the PSD of the first term, which is just an impulse, PSD of second term, which is an amplitude modulated signal. So the total PSD of the output we can find by just adding the PSD of the two terms. So we want to find PSD of output. The first term is going to have an impulse with a strength of a square by 2. The second term is going to have amplitude modulated PSD. We have strength of a square by 2. S phi n. Now we can see that if there is a phase noise present in the output of the oscillator, its output is going to have this kind of side skirts because of the PSD of the phase noise. So this is what we are going to see in the actual measurement also in the lab. If we feed the output of the oscillator to a spectrum analyzer, then it is going to show this kind of side skirts. So here we can see that if we want to find the PSD of the phase noise, then we can simply find what is the noise PSD at an offset from the center frequency omega naught and normalize it with the signal power at the output of the oscillator. Implies the phase noise PSD at a frequency offset, let's say delta omega from omega naught, is nothing but, say this is the offset we are talking about. So this phase noise PSD is going to be equal to just the noise PSD at the offset normalized by the signal power of the oscillator. So this is going to be a square by 2 phi n by a square by 2 is equal to the PSD of the phase noise. And we can see that in general this phase noise is going to have a frequency dependence as we move away from this omega naught. So the phase noise is measured in this way, which we have seen, and it is always mentioned at a frequency offset, and this frequency offset delta omega, which we showed earlier, is converted into hertz. Frequency offset of delta f, we try to find what is the noise PSD at this offset delta f, which is same as trying to find what is the noise power in a 1 Hz bandwidth at the offset delta f from the center frequency. We find out the noise power in 1 Hz bandwidth at delta f offset from carrier frequency. So this omega naught equal to 2 pi f naught normalized to the signal power, which in our case is a square by 2. And then we take a 10 log of this ratio to convert into decibel scale. The units for this phase noise is dBc per hertz. dBc, to emphasize that we are taking the ratio of the noise PSD with respect to the carrier power. With respect to carrier power.